Let's finish this with the law of cosines. So what I have so far on display here, I have set up my triangle in this form in the first quadrant. Angle C is an acute angle. What I'm doing will work, by the way, whether C is acute or obtuse. Either way it works. So what are we looking at here? We're looking at the case where we have two sides and included angle. Okay, so let me actually go SAS for this one. Two sides and an included angle. In this case, my two sides are A and B. The included angle is angle C. All right. Now, from the geometry of what we're looking at, we can form sine of C, sine of angle C, as the ratio of opposite y to hypotenuse would be A. Correct? So from this, we can say that y is equal to A sine C. And then we can do cosine of C as the ratio of x to A, and we can say x is A cosine C. So the coordinates of point B as a point on a plane would be xy, and the coordinates of B, therefore, are going to be A cosine C, comma, A sine C, right, based on what I just did here. Now, having this, we can actually use Pythagorean, okay, Pythagorean, and write this relationship. We know that C squared is going to be B minus X squared plus Y squared, right? We can write that. Again, C is the length of that side is equal to B minus X. Now I'm looking at, actually, let me draw what triangle I'm looking at. I'm looking at this triangle. Here's B. This is A, and here's Y. This distance is actually B minus X. I'm looking at this portion, right? Remember, this is X. That is X. So this side is going to be B minus X because the distance, the coordinates of point A are B comma 0. So the length of the side, this side is going to be B minus X. Okay, and that's the C part. Now, I can replace X with A cosine C, couldn't I? Right here, that's X, and then we're going to change Y with A sine C. So we're going to get B minus A cosine C quantity squared plus A sine C quantity squared. Now if I square the binomial, I get C squared is E squared negative twice AB cosine of the angle C plus A squared cosine squared C. And then A sine squared becomes A sine C squared becomes A squared sine squared C. Here we can factor A squared from the last two terms, and once we do, we get sine squared plus cosine squared C, right? Once we factor A squared, and we know that by Pythagorean identity that's 1, so we can in turn write that as A squared plus the other two terms, 2AB cosine C. And this is indeed one version of the law of cosines. Okay, so if you need to find the measure of a side, let's say given two sides and an included angle between them, this is how we can find the length of the other side. Okay, and then to find the measure of the angles, we can use the law of sines to do that, because by then we have all three sides and an angle, we can use the law of sines. Okay, now, by the way, if C is the right angle, see right in here, I have an acute angle, And as I mentioned, this derivation also works if C is obtuse angle. But if C is a right angle, what's going to happen is this. Let me write. If C equals 90 degrees, if the measure of angle C is 90 degrees, it's a right angle. So this becomes C squared A squared plus B squared minus 2AB cosine of 90. And we all know cosine of 90 is 0, which makes that 0. Therefore, for a right triangle, we get the familiar Pythagorean theorem. There you have it. Given two sides, we can find the third side using Pythagorean. So in other words, Pythagorean theorem is a special case of the law of sines. The law of cosines. Okay, let's take a look at an example here. So suppose I'm going to make up two sides to be 3 and 4. The measure of angle C, we're going to make that 40 degrees. Again, I'm given two sides and an included angle. So the geometry so far looks like so. Here's 40 degrees. Doesn't matter how you put the size, the two sides. Let's say this is 3, this is 4. The longer side is 4, the shorter is 3. And we want to find the length of this side. Okay, and I'm given capital C is 40. Little a is 3, so this is cap A. Little b is 4, this is cap B. Great. So we can find the length of C as C squared equal A squared plus B squared. Sum of the square of the other two sides, negative twice the product times the cosine of the included angle. And that's it. I just have to plug in the numbers 3 squared, 4 squared, negative 2 times 3 by 4, and then cosine of 40 degrees. So that C squared ends up being 6.6, and C, we take that to be the positive, the square root of 6.6, or in this case, 2.57. And the law of cosines. And by the way, the law of cosine is quite useful, and is used quite often in applications in engineering sciences and in also vector analysis. All right, so we have that one. Then we found a measure of C. So all sides are known now. It's 2.5734. Now to find a measure of angles, we can use the law of sines. We have 3 sides, so let's choose the one, in this case, sine cap A over 3 is equal to, I definitely want to use sine of 40 degrees, the only known angle, over 2.57. And from this, see, we can solve for sine A, multiply both sides by 3. That's 3 sine 40 divided by 2.57. And let's see, this turns out to be 0.7503. And then A is simply the arc sine of that number, 7503. And that gave me a measure of the angle as 48.6 degrees. And that's the measure of angle A. Once we have that, measure of angle B is 180 minus the sum of the other two, the 40 degree and the now found 48.6 degrees, and the whole thing ends up being 91.4 degrees. There we have that one. So we solved the triangle. If we have two sides, it's again really easy to find that third side. Now let's change this slightly. My next example, suppose A is 6, B is 11, and this time actually suppose we're given that other side. So all in all, I have 3 sides. No angles. So for this one, we can go with either C squared or A squared or B squared. If I go with the c squared version of the law of cosines, is c squared is a squared plus b squared minus 2ab cosine c. Again, the other two versions are this: a squared is b squared c squared, sum squared the other two sides minus twice their product, cosine of the included angle. Or if you want in terms of b squared is a squared c squared negative 2ac cosine of the included angle b. The little b cap b go together. See, little a cap a go together there. These are again alternate version of the law of cosine, depending on which two sides are given. Okay, so I need to find the measure of angle C, right? Capital C. So I'm going to solve this equation for cosine of cap C. When I do, I get a squared plus b squared minus c squared divided by 2ab. You can try that. It's not difficult. Bring a squared b squared to the other two sides. They both become negative. Then divide by negative 2ab. That's what you get. Okay, and now all I have to do is plug in the specifics. I can actually even go a step further. Let's do this. From this, take arc cosine of both sides, or by definition of inverse, therefore cosine inverse of cosine inverse. C is cosine inverse of the right side, a squared b squared minus c squared divided by 2ab. All right, and let's do it now. So the whole thing in one pass in my calculator will work this way. 6 squared, 11 squared, negative 12 squared, divided by 2 by 6 by 11. And this will give me the arc cosine of 0.0985 is what the whole content of within the bracket would be, and arc cosine of that's going to be 84 degrees, 0.34 degrees. Okay, so that's the measure of angle C. We found one angle. Now, and remember, we were given the other angle was 90. Oh, no, I'm sorry. That was the very first angle we found. Okay, so let's find the other angle. Now, for the other angle, again, you can use this. You can say B is cosine inverse of a squared c squared minus b squared over twice ac. You can do that, or you can use the law of sines. Cosine inverse, either way is fine. It's just a matter of preference at this point. That's 36, that's 6 squared, 12 squared minus 11 squared divided by twice 6 by 12. And this is going to make it 65.8 degrees. So we got 2 out of 3 angles. So angle A, measure of angle A is going to be 180 minus B minus C. And that will do it for us. B is 65.8, and the other angle was 84.34, angle C. And I got the measure of angle A to be 29.86 degrees. Okay, so the 3 sides are given, and that's what it turns out to be. All right. So hopefully you can follow this. It's really not bad. You don't have an ambiguous case. Like in the case of law of sines, the ambiguous case is something that you gotta watch out for. Let's take a look at maybe a couple of application problems, and then we'll be done with this section, rather a short section. So let me bring up my application here. All right, our first example here is from navigation. The question reads, an airplane flies due north from Fort Myers to Sarasota, a distance of 150 miles, and then turns through an angle of 50 degrees and flies to Orlando, a distance of 100 miles, according to the figure. In part A, how far is it directly from Fort Myers to Orlando? So we want to find the direct distance from Fort Myers to Orlando. Call that D. Now, from the triangle here, we know that this angle has to be, 130 degrees, because combined with a 50-degree angle, they form a straight angle. That should be 130 degrees. And from that, that's all we need. We can actually set up the law of cosines because we are given two sides and the included angle. Therefore, the side that we're looking for in part A, I can say d squared is equal to sum of square of the other two sides, correct? Negative twice their product times the cosine of included angle, 130 degrees. So you work this one on the calculator, you're going to get a very large number in the millions. And then take the square root of that number, go with the positive root because distance is positive, so we keep the principal root. And the distance d is going to be 227.6 miles in this case. That's the direct distance from Fort Myers to Orlando. In part B, what bearing should the pilot use to fly directly from Fort Myers to Orlando? The bearing that they're talking about is this one. This is the angle theta. Now in navigation, the bearing has to do with the angle that is formed from a north-south. Let me draw my compass here. So I have north, south, east, west. Okay. This is the bearing theta. Angle theta, when in navigation and using bearing to state it, theta is acute. Keep that in mind. It can never be an obtuse. It's an acute angle. Okay. So if the angle is, for instance, in the first quadrant, as you can see here, then whatever the angle is, we say that the angle theta is so much, like so many degrees east of north. So it's going to be east, and then you state the measure of the angle, and then north. So that's the measure of angle theta, that is east of north. If the angle is in like the third quadrant here, call it alpha. Well, this angle alpha is west of south. So the angle alpha is west of south. So the first letter indicates the east or west side, and the second portion indicates the north and south. Okay, so for this one, I need to find the measure of angle theta first, and I'm going to use the law of sines. So I can say that sine of theta over 100 is equal to sine of 130 degrees over 227.6. Okay, and from this, multiply both sides by 100 and do the calculations. I got sine theta to be 0.3366. And theta would be the arc sine of 0.3366. So the measure of angle theta turned out to be 19.67 degrees. Okay. And again, in terms of bearings, we can say the bearing of that airplane is 19.7 degrees east of north. East of north. In other words, here's how we're seeing that. This is the measure of angle. That's 19.67 degrees. Here's north. There is east. So the way to write it is such. North 19.7 0.7 degrees east. Okay. And if I do that, I can actually switch these. There you go. I can write this as northeast, and this would be south and west. There you go. So let's put actually north south first, and then east west second. So it's going to be north or south. That's the first letter, and again the second letter could be east or west. There we have that one. Okay. So we're good with this exercise. Now let's take a look at another example here. This one is interesting too. For this example, we were told that the height of a radio tower is 500 feet. So we know that part. The ground on one side of the tower slopes upward at an angle of 10 degrees. Okay, and in part A, notice on the left side it does not angle, it's flat. In part A, how long should the guy wire? The guy wire is what's kind of holding the tower, so it doesn't have to wobble. That's what the guy wire is. How long should the guy wire be if it's to connect to the top of the tower and be secured at a point on the sloped side 100 feet from the base of the tower? Okay, so if we do this now, remember to the base complete, that's 90 degrees. Because of that 10-degree slope, therefore the measure of the angle here, let me use red. The measure of this angle is going to be 80 degrees, right? All right, and again, because this is how it works, we have, this is a right angle, but then we have a 10-degree slope on the hillside, right? Right here, that's 10 degrees, so that means the remaining portion should be 80 degrees, and this is, call it G for the guy wire, or L for the length. How's that? L for the length of the guy wire. In part A, we're given the height is fixed. Height of the tower is 500 feet. That's not going to change, and we are good with that one, right? And we are also, let me remove that because I lost it right in here. We're given the length of the side is 100 feet. And therefore, this is 100 feet. That's the length of the side. Perfect. And with this, we can use the law of cosines because we have two sides and an included angle. So I'm going to say that L squared is equal to the sum of squares of the other two sides. Negative twice their product, and cosine of included angle, cosine of 80 degrees. And again, if you work this one, once you take the square root, the number itself ends up being quite large. Okay, it's like about 200. Let me put the number I got. L squared turns up being 242,635.1822. There you go. 242,635 and change. So L would be the square root of this number, which is 492.58 feet. So that's the length of the wire that's necessary for that portion. Now, on the other side of that one, part B. In part B, the question is, how long should second guy wire be if it is to connect to the middle of the tower? Okay, the middle of the tower, so the triangle now looks like this. The middle of the tower, so the height of the tower at that point is going to be 250 feet because it's the middle of the tower. And this is the length that we need. Call it whatever. Maybe, I don't know, capital L. because I used a little L earlier. All right, so this is going to be 250 L, and this distance is given to be 100 feet. That's the right angle. And for this one, we just use a straight Pythagorean, right? Because it's a right triangle. Therefore, we're going to say L squared is equal to sum of squares of the other two sides. Therefore, the length of the guy wire on the left side is 269.26 feet. And there you go. And you can see that again, the law of cosines is pretty straightforward, nothing drastic. And we are done with this section, and in fact we're done with the chapter now. Rather short chapter. We only covered 3 sections. We did law of sines in the previous lecture, and now the law of cosines. All right, hopefully everybody's good on this lecture. And thank you for watching, and we'll have you in another video, another lecture.